would like to start talking today, is different aspects of ferromagnetism. First of all, I would like to introduce ferromagnetism from the perspective of statistical mechanics. In other words, I would like to introduce the concept of ferromagnetism from the perspective of the symmetry, breaking, and the order parameter. Alright, so in order to introduce this concept, suppose I have a mass, certain mass, say m, and this is placed on a strut. Such a strut is generally referred to as an Euler's strut, in honor of the scientist or mathematician who studied this first. Now, if this strut is vertical and this is ground and the mass is symmetrically placed on top of this strut can withstand the stress that is induced inside the strut because of this heavy piece. However, if I keep on adding mass to this object, I add some mass, still the strut remains vertical, because the stress inside the strut is within the Young's modulus, is within the limit, the elastic limit of this strut. So it's not going to break, it's not going to buckle. Now I gradually keep on adding mass to this system. At one point, this strut will start to buckle. Now there are different possibilities. One possibility is that this strut buckles to the right. The other possibility is that the strut buckles to the left. Now the strut has to buckle to either to the left or to the right. Now you can argue that if I actually place this mass symmetrically and I control the environment in such a fashion that there are no air currents and this mass is perfectly symmetrically placed on top of a perfectly machined Euler strut, then would such a scenario arise? Yes, the scenario would arise even if we perfectly balance this mass on top of the strut and everything is symmetrical. So what we have in this scenario is something that is symmetrical. The high order of symmetry here. But at a certain critical value of mass, when the m exceeds a critical value, the symmetry is broken. And you get either a right symmetry or the left symmetry. From the perspective of the isotropy of space, there should be no difference between right and left. What determines whether the strut moves to the right or the left? So at a certain, beyond a certain threshold, which is a critical value for the mass, symmetry is broken. And when symmetry is broken, order is introduced. So this is right order, this is left order. Now, consider, for example, we would say that a phase transition has occurred. And that accompanying that phase transition, there is a breakage of symmetry. Symmetry has broken whenever a phase transition has taken place. The symmetry of the system has changed. In fact, when you go from here to here, the symmetry is broken. Suppose you have a gas or a liquid. Now, the molecules of the liquid or the gas, they are undergoing translational motion in all possible directions. This is our scenario for a fluid. Whereas Whereas in a solid, if we lower the temperature and the temperature is below some critical temperature, you will see ordering of everything freezes and you see ordering of the atoms. Now don't take these arrows literally, I'm just representing atoms by arrows. So the atoms freeze in a certain position and everything looks ordered. However, from a symmetry perspective, this is a state of high symmetry. Because if you stand at any point and if you look around, all the directions are the same. And if you change your position inside this fluid, inside this container, and you look around, all the directions are the same. So all of this space, all this condition is one of high symmetry. You have perfect rotational symmetry in this case. However, if you make a solid, and inside your solid, if you have a square lattice, then of course it's not rotationally symmetric. For example, if you stand at one point and look in this direction, it's not going to be the same if you look in this direction. So isotropy has been compromised here. The symmetry of this system is lower. In fact, if this is a square lattice, the only possible symmetry operations are rotations, four-fold rotations about the z-axis. So you could have a four-fold rotation, you could have a two-fold rotation, you could have three, four-fold rotations. That is, you could have rotations of 90 degrees, 180 degrees, 270 degrees, 90, 180, 270 and 360 degrees, which is doing nothing. So these sets of operations are the only symmetry operations that are valid for this solid. Now a phase transition has occurred that has converted a system of high symmetry to a system of low symmetry. So with every phase transition, there is a breakage of symmetry. The symmetry is compromised. Likewise, if this were a paramagnet, now the same diagram applies to a paramagnet. Now these are spins pointing in different directions. This is a highly disordered state, but it is highly symmetric. Now if you go below the Curie point for this material and a ferromagnetic state is achieved, then you have broken the symmetry. Now all the spins are pointing in a preferred direction. So it's not symmetrical. All the directions are not the same any longer. You have chosen or picked up a unique axis inside this material. So symmetry is now broken. Breaking of symmetry means that certain directions are preferred over the others. In this case, all directions are on equal footing. So this is an isotropic case of high symmetry. Now when a ferromagnet has been achieved, symmetry has been broken. And this transition from the paramagnet to the ferromagnet occurs through a critical point, which is called the critical temperature. Now, we can also draw phase diagrams. We all know that we can draw phase diagrams. So we can draw a phase diagram for water, for example. If I take the temperature here and the pressure here, we're all familiar with the phase diagram for water. Okay, this regime is the regime of, this is the solid, this is the liquid, and this is the gas. Okay, we know that this is the triple point, about 273 kelvins, this is some critical point about 670 kelvins. Now if you go from the liquid to the gas state, there is no change in the symmetry. However, if you go from the liquid to the solid state, or from the gas to the solid state, symmetry is broken. So certain phase transitions are associated with breaking of symmetry and certain phase transitions are not associated with the breaking of symmetry. Beyond the critical point, if you move from here to here, then there is no phase transition that takes place. This is not a phase transition, there is only a density variation here. So you can draw phase diagrams for magnets in the same manner. Paramagnetism, ferromagnetism, antiferromagnetism correspond to different phases of the magnetic properties of a material. And we found out that the Curie points and the nail points are definite temperatures. They are deduced theoretically, they are predicted theoretically, and they are also determined experimentally. So at a certain precise temperature, at atmospheric pressure, a phase transition may occur from a ferromagnetic to a paramagnetic state, which is called the Curie point, from an antiferromagnetic to a paramagnetic state, which is called the nail point, etc. Now the question that I would like to answer is, if I have the ferromagnetic state, all the spins are perfectly aligned. Okay, it's a perfect ferromagnet. The temperature is below the Curie point. Now this is a state of low symmetry, high order but low symmetry. Now when you cool a paramagnet to below the Curie point, so you move through the Curie point, so it's hot, so it's a paramagnet, you cool below the Curie point, it turns into a ferromagnet. Which of these states, and suppose you're at zero, you're inside zero magnetic field, so you're only talking about spontaneous magnetization. Which state will the material acquire? Will it acquire this state, or will it acquire this state? Both of these states are equally likely. So this is exactly analogous to the strut example that I presented on the top. You're putting mass on a strut. You keep on increasing the mass. Beyond a certain critical point, either you get the right configuration or you get the left configuration. Who decides this? The right and the left are equally likely. Now symmetry is broken. One of the choices is picked up. Who decides this? God? No. There has to be some physical explanation for this. Now, in order to describe this process from a statistical mechanics perspective, let me talk about the ammonia molecule. Now, what's the connection? If I have the ammonia molecule, so this is nitrogen and a lone pair of electrons and bonded to 3 hydrogen atoms. Okay, so this is one configuration of the ammonia molecule. The other configuration is that the plane in which the hydrogen atoms lies is above the nitrogen, and this is the configuration where the hydrogen atoms lie in a plane that is below the nitrogen atom. Let's call this configuration Ket 1 and let's call this configuration Ket 2. Now this is a pyramidal molecule. Suppose this is like an umbrella. Wind blows and you get the umbrella inverts itself. So both of these configurations for the ammonia molecule are equally likely. Now if you plot the potential energy versus x. Now what is x? X is, suppose, the distance of the pyramidal plane with the nitrogen atom. Now both of these configurations are equally likely, so you will have a double potential well, like this. So this is x naught, this is minus x naught, which means that this is, say, x naught, this is minus x naught. So the potential energy graph for the ammonia molecule should look something like this. You have two values, you have two minima. And this, one of the minima corresponds to Ket 1, the other minimum corresponds to Ket 2. Now if you look at the Hamiltonian for this system, the Hamiltonian for this system you learn from quantum mechanics is some E naught and there is some transfer amplitude here, which helps you interconvert between the states Ket 1 and 2. Now if you look at this Hamiltonian, this state is not an eigenstate of this Hamiltonian, neither is this state. So if you prepare your molecule in this configuration, and this is the Hamiltonian of the system, gravity oscillations will occur. Interconversion between the ket1 and the ket2 state is going to occur at a certain frequency, which is determined by this constant T, this transfer amplitude. So the frequency with which 1 converts to T and 2 converts back to 1 is determined by these off-diagonal terms in the Hamiltonian. Alright, this means that if you prepare the ammonia molecule in this state and leave it, it's going to resonate between these two configurations. Rabi oscillations will take place with a certain frequency. Smaller this value of T, the longer it will remain in this state. But it is gradually oscillating between the two configurations. So if I plot time here, and I have a quantum state psi, which is some C0 ket1 plus C1 ket1 plus C2 ket2, which tells you the state of the ammonia molecule. Then with time, what's going to happen if I plot the probability of obtaining state ket1, which means the projection of the state on ket1, I will get a cosine square curve. And if I plot the projection of the state on ket2, I will get a graph that is 90 degrees out of phase, depending upon where I start. So there is continuous oscillation between ket1 and ket2. And ket1 is not a stationary state. If you prepare this state, it's going to transform into this state. Okay? Now, there is a certain time period associated with this oscillation. After a certain time, ket1 will interconverge to ket2. This means that this process has a certain frequency. That frequency is the inverse of this. You solve the time-dependent Schrodinger equation with this Hamiltonian. This is the kind of dynamics that we will obtain. Alright? For the ammonia molecule, this frequency is about 24 gigahertz. Now, associated with this frequency, I have a time period, which is the inverse of this frequency, is of the order of picoseconds here. So the oscillation between the two conformations of the ammonia molecule takes place on the scale of picoseconds. Now, if I replace this ammonia molecule, inside the ammonia molecule, I replace this nitrogen with a phosphorus. I get phosphine. Now, in this phosphine gas, the phosphorus is much heavier than the nitrogen. So the frequency decreases and the time period goes up. So if I replace the nitrogen with the phosphorus, then what's going to happen is that the frequency of oscillation goes down. Just as you have a spring, omega square is k over m. You increase the mass, the natural frequency goes down. Likewise, in this system, if I use a heavier atom here, the frequency of oscillation goes down. Okay, by the way, this frequency of 24 gigahertz is used to measure the concentration of ammonia in the environment, or amines in the environment. It's used for environmental detection as well. Anyway, I replace this nitrogen with phosphorus, I can decrease this frequency and increase the lifetime of a state. Even though the state is not an eigenstate, but its lifetime goes up. You can get a metastable state. Exactly this is what happens for a ferromagnet. In a ferromagnet, this configuration, if I call this ket1, is equally likely as this configuration, which I call ket2. There is no difference. Both of these states have the same energy. Remember, I am not imposing an external magnetic field. So there is really no uniqueness with this state. This state is at par with this state. However, once you prepare this state is not an eigenstate of the Heisenberg exchange Hamiltonian. It's not an eigenstate of the Ising Hamiltonian. It's an eigenstate of the Eigen-Hamiltonian, but not an eigenstate of the ferromagnetic exchange Hamiltonian, the Heisenberg Hamiltonian. So this state is going to oscillate to this state, and this state is going to come back. However, the lifetime of each one of these states is larger than the age of the universe. So it's an extremely slow process. Okay, in other words, if you make a potential well for this configuration, you will get a steep valley. And the probability of tunneling from this state to this state is going to be vanishingly small. Alright? So both of these states are equally likely. Neither of them is an eigenstate of the exchange Hamiltonian. So once you prepare one state, it remains there. But it's an identical twin to the other state. If you prepare this state, it will remain there. Because the transition, the oscillation to the other state is so slow that it would exceed the age of the universe. It's so large. Okay? Now this is a basic concept of how ferromagnetism is related to symmetry. Whenever you have a phase transition, symmetry is broken. Some kind of symmetry is broken. And we can in fact formalize this discussion further using a famous theory which is called Landau's theory. Now Landau's theory is a popular theory in statistical mechanics that can explain ferroelectricity, it can explain crystallization, it can explain liquid crystals. Whenever a phase transition occurs, that is, you go from an ordered state to a disordered state, or from one kind of ordered state to a disordered state, Landau's theory provides a nice framework. It can also explain superconductivity. Now what is Landau's theory? And what do ferromagnets have to do with this? In Landau's theory and in the concept of phase transition, we can associate an order parameter with different phases. Some order parameter. For example, when we study magnetism, a convenient order parameter is the magnetization. For a ferromagnet, from our basic knowledge of the Weiss's molecular field theory, we know that if we have temperature here and we have magnetization here, above the Curie point, the magnetization is 0. And below the Curie point, the magnetization goes up. So above the Curie point, the order parameter is 0, and it suddenly becomes non-zero when a new phase has been entered. So the order parameter in the case of magnetism is magnetization. It's a convenient order parameter. For superconductors, it's going to be different. For ferroelectrics, it's going to be different. All right. Now, we can also define a free energy, which is going to be a function of magnetization. And if we talk about the Helmholtz free energy, it is U minus ds. You all know that. We also have the Gibbs energy, which is H minus ds, which is U plus PV minus ds. But if the pressure is small, if this term is small, then the Gibbs free energy is the same as the Helmholtz free energy. So we're going to use this parameter here. Okay. Now, as we've noticed that for a ferromagnet, if you have the magnetization in the up direction or in the down direction, the energy of both of these configurations must be the same in the absence of a magnetic field. Therefore, if you would like to expand this free energy as a function of m and temperature, then it must be a series that comprises even powers of m only, because we would like to have f at minus m the same as f of m. means f is an even function of n, and that is ensured only when this power series expansion contains only the even powers of m. So we can approximate this f by some f naught plus some parameter a m square plus b m4, and we truncate this approximation over here. Now we have to put in temperature somewhere. So this is a constant. These m's can depend upon temperature. Let's make this parameter temperature dependent as well. Alright? Remember, when we talk about the Helmholtz free energy, if we are at low temperature, remember that for a system to be in equilibrium, the free energy has to be lower. If you are at low temperature, then this term is almost zero, and you can lower F by lowering the energy of the system. If you are at high temperature, then this term can no longer be neglected. It dominates. And then at high temperatures, you can lower F by increasing the entropy of the system. So at high temperatures, you lower the free energy, the available energy, by increasing the entropy of the system. Whereas if you're at low temperatures already, you lower the energy by reducing U. So F can be reduced by reducing U or increasing S. If you're at high temperature, this term is going to dominate. And if you're at low temperature, then this term is going to dominate. Okay. Now we have this. This is what was proposed by Landau as an expression for the free energy of a sample with magnetization M. And the point is that we would like to lower this energy. Okay? And we would like to see if a phase transition comes out of this model for the free energy. If this gives rise to some kind of order parameter which has the property that the order parameter is 0 in one state and it's non-zero in the other state. And there's a cutoff at which the order parameter goes to 0. So we would like to see whether this kind of free energy can give rise to a graph like this. Right, this is the point. This is a graph of the order parameter, which is the magnetization. Can this theory give rise to an order parameter that varies with temperature like this? The order parameter is 0 above a critical point and it's non-zero below the critical point. This is what we would like to see now. So the proposal is, you see this is a proposal. The proposal now is that this B is positive. M can of course be positive or negative. This AT is equal to some positive constant. This is positive. T minus Tc. Tc is some critical temperature if it exists. If temperature is greater than Tc, A is positive and vice versa. If T is less than Tc, this thing is negative. So this is our model here. Alright, now what we would like to do is we would like to minimize the free energy with this model, with Landau's model, and see if it gives us a phase transition and if it gives us a convenient order parameter. So let's minimize this free energy with respect to temperature. So this is independent of temperature. Let's minimize this with respect to the magnetization. So this is independent of magnetization. This is just a constant. I get 2ATM here plus 4BM cube. Alright, so I equate this equal to 0 and I obtain 2A naught T minus Tc over 4B equals m squared. So I'm keeping the temperature constant. So this is an isothermal calculation for the time being. I'm seeing what happens at constant temperature, at some temperature T. And you'd like to see what's the relationship of that temperature with Tc and how does it change m. Because m is our order parameter. So I'm varying the order parameter here. I'm finding the change in the free energy with respect to the order parameter, which is m. Okay, that's why I differentiate with respect to m. M is my order parameter. I would like to vary m here. I would see how the m changes at some temperature. What's the value of m at some temperature? So the energy is minimized when this condition is satisfied. In other words, when m equals A naught over 2b 1/2 T minus Tc 1/2. Now if I look at the equation over here, I have m 2AT plus 4B m square is 0. So there are two possibilities. One possibility is that m equals 0. The other possibility is what I've written over there, that m equals plus minus, will be plus minus A naught over 2b 1/2 4b m square is minus 2A naught T minus Tc. This is 2A naught Tc minus T. M equals A naught over 2b Tc minus T. So this is Tc minus T 1/2. So the energy is going to be minimized when this condition is satisfied or when this condition is satisfied. Either one of them. Alright? Now let's understand this further. What I've done, I've written the free energy as an even function of the m's. I've differentiated the free energy with respect to the magnetization and I get two possible solutions. Now if my temperature is greater than Tc, can this solution work? So I have to choose which solution do I pick. If my temperature is beyond the critical point, is this a physically meaningful solution? No, because inside the under root you have a negative term. So when my temperature is beyond the critical point, the only possible solution is n equals 0. And if my temperature is below the critical point, I can have this solution, the magnetization can be 0. Then I'm not dealing with the magnetic material, but I can also have a non-zero magnetization, because now this temperature is smaller than Tc, this is positive, the square root of positive terms is permissible, so I choose either the plus or the minus, it doesn't matter, because both of them are on equal footing. So the magnetization becomes plus minus A naught over 2B 1/2 Tc minus T 1/2. So now I have figured out that my ordered parameter takes a sudden change when the temperature crosses Tc. If the temperature is beyond Tc, the order parameter suddenly goes to 0, and if it is below Tc, it takes up this functional form. So if I would like to plot this is T over Tc, this is M over Ms, the reduced magnetization. Above the critical point, the magnetization or the order parameter is 0, and here it takes up a form that is given by Tc minus T raised to power 1/2. The magnetization is described by a power law. Square root dependence upon the temperature. Here remember Tc is greater than T in this regime. So this magnetization obeys a power law. And this theory gives us a power law for the magnetization below the critical point and the order parameter is 0 above the critical point. And the exponent in this power law is a special property of this model. This model proposes that this exponent in the power law is 1/2. Such an exponent is called a critical exponent. Different kinds of models will give different critical exponents. And when you plot the magnetization experimentally versus temperature, the exponent that you get for the data will not exactly be equal to the critical exponent, but it's going to be similar. And if it's 1/2 or close to 1/2, you'll say that the Landau model is a good description of the behavior of this material. Remember, when you have low temperatures, you have magnons, you have spin wave excitations. And in that case, you cannot use such a theory. This is a mean field theory. Now let's look at the magnetization. Look at this magnetization over here. This magnetization gives a power law dependence on the temperature beyond the critical point. But the important point is that there is some critical temperature, and the phase transition occurs at this critical temperature. So the phase transition actually stems out of this Landau model automatically. Now suppose what I do is the following. Suppose I impose a magnetic field now, and I would like to see what kind of free energy should I write, and what other critical exponents, what other power laws come out of it. Summary. Associated with the phase transition is a sudden change in an order parameter. The Landau's model is one model that gives you a phase transition. Alright, above the critical point, the Curie temperature, the order parameter is 0. Below, it varies in the form of a power law. The exponent in the power law is 1/2 for this model. In fact, for any mean field model, it's going to be 1/2. Now let's impose a magnetic field. If we impose a magnetic field, then what's going to happen? The free energy is going to change. It's going to be F naught plus A T M square plus B M4 plus an additional term due to the placement of a magnetization inside a magnetic field. From electrodynamics, we know that this is going to be equal to minus Bm, right? Now you look at this term over here. Now what I would like to do, I would like to find out the minimum in the free energy. That's of course 2A naught T minus Tc M plus 4B M cube minus B. I would like this to be 0. Alright, so one corollary of this is that if I am at Tc and I have imposed a magnetic field, then this term equals 0 and I have energy will be minimized when 4B M cube is B. B is mu naught H. That is the magnetization at the Curie point scales as H raised to power 1 over 3, where H is the applied magnetic field intensity. So this is another power law. The first power law states the magnetization as a function of the temperature in the vicinity of the Curie point. This is another power law which states how does the magnetization change with the applied magnetic field. Of course, this is also going to be equal to B raised to power 1 by 3 because H and B are proportional. How does the magnetization change with the applied magnetic field? And the change is given by H raised to power 1 over 3, another power law. This 3 is also a critical exponent. So any mean field theory will give you certain critical exponents, certain power laws. One of them is that the magnetization varies as Tc minus T, some power law, some alpha here, where alpha is given by 1/2 for a mean field theory. Another power law is the magnetization varies as H raised to power 1 over delta, where delta is 3. It's another critical exponent. You can also have the susceptibility. This is something we've already seen. The susceptibility varies as T minus Tc is for minus beta, where beta equals 1. This is the Curie-Boyce law. So all of these are power laws. Any mean field theory will give a power law dependence of the magnetization of with respect to temperature, the magnetization with respect to field at a constant temperature. So this is called an isothermal power law. It's a constant temperature. It tells you the variation of magnetism with the applied field. You can also have a variation in the heat capacity with T minus Tc. This is something we're going to derive today. So all of these are power laws, and this Landau theory gives you certain values of exponents for the behavior of these properties with respect to temperature or applied fields. Now let's move back to this expression over here if you look at this expression and we divide both sides by m, I get 2a naught t minus tc plus 4b n square equals b over m. This means n square is minus 2a naught over 4b t minus tc plus b over 4bm. Okay, this is just algebra over here. This is a naught over 2b tc minus t plus mu naught over 4b h over m. This is my m square. Now this relationship tells us that if I were to make a plot between n square and h over n, I will get a straight line. The slope of this line is a constant, mu naught over 4b, and the intercept of this line changes with the temperature. Now if I make this plot over here, that is, I make a plot between h over m and m square, I'm going to get a straight line. If my temperature equals the critical temperature, the straight line is going to pass through the origin. If I'm at a slightly higher temperature, then this will be my line. If I'm at a lower temperature in the critical point, this will be my line. So this line corresponds to temperature equals Tc. This corresponds to the temperature greater than Tc. And this region corresponds to temperature smaller than Tc. So what you could do, you could perform an experiment in which you measure the magnetization, square it, and plot it versus the applied field divided by the magnetization. The slope of this line remains constant. The intercept will give you the Curie point. Okay, so this is one method of determining the Curie point. There are many methods. This is one of them. Such a plot is called an Arott plot. And this is what experimenters use all the time to determine the Curie points. Let me give you an example here. So if you observe here, there is m square conventionally measured in EMU, electromagnetic units, the CGS unit for the magnetization per gram. Okay, because the magnetization is independent of the mass or volume of the object. Okay, EMU is the unit for the total magnetic moment. So magnetic moment divided by volume or divided by mass. You can use either one of them. So on this axis we have m square. On this axis we have h over m. All of this is in CGS units because it's still popularly used. H is measured in Orsteds, m is measured in EMU per gram. So this is a result of the magnetization measurement for this particular compound, a samarium compound, just published this year. This is low temperature measurement. temperature is going up. So each one of these curves is an isothermal magnetization curve. It's measured at a single temperature. And what's the variable? The experimental variable is this H. So H is varied, the applied field is changed. When the applied field is changed, the magnetization is measured using some methods, using a magnetometer, for example. And the data is then plotted. As you increase the temperature, you are increasing the temperature, the lines are moving downwards. The intercept is becoming more and more negative. So from this data, you can actually determine that the Curie point lies somewhere between 5.5 Kelvin and 5.75 Kelvins. Because this line has an intercept that is negative, this has an intercept that is positive. So zero intercept would lie somewhere in between. Alright? So this is an example of an Arott plot, which is used all the time for measuring the Curie point. This is just one method. So this is another method in which the axis has shifted. M squared versus H over M is just now shifted. They just shifted the axes, and exactly the same behavior is observed as we observe over here. Alright, so these kinds of measurements are done all the time in order to determine the Curie point. Now what I would like to talk about is, I'll have more slides to show, but before that I need to discuss some more things. Now what I would like to do is, I would like to plot the free energy, this energy that I've written over there, F as a function of magnetization and temperature, F naught plus A naught T minus Tc M square plus B over M4. So I'd just like to plot this free energy as a function of M. In the vicinity of the critical point, which means that this is the variable, this is my parameter. M is the variable, this is my parameter. I would like to change the temperature slightly and see what kind of free energy curve do I get. In order to do that, let's move on to Mathematica. It's a simple calculation over here. If I take my F naught, if I ignore F naught, if F naught is 0, I can plot. Now I take T greater than Tc. So first of all, suppose I'm at the critical point. I'm at the critical point, the second term is 0. So I just want to plot m raised to power 4 with respect to m. So this is my free energy curve over there. On the horizontal axis I have the magnetization, and on the vertical axis I have the free energy. So the free energy is minimized at m equals 0. So the minimum of this function is m equals 0. If I zoom in a little bit, I plot from -1 to +1. zoom in further. So the minimum is precisely at n equals 0. So the free energy is minimized at the critical point. The free energy is minimized, which at magnetization equal to 0. Okay. I can also compare this with the parabolic curve. I can compare this with m squared. You see, this is the m squared graph. This is the graph that includes, this is the M4 graph. The M4 graph is much broader. So there is the possibility that the magnetization can vary by large amounts without changing the free energy. So near the critical point, large fluctuations in the system can take place. And those large fluctuations can increase the correlation length scale inside the material. Okay? The long range order can be introduced inside the material. In other words, the material is at the brink of a phase transition, it's just at the verge of a phase transition. The system is becoming more prone to large fluctuations. You see, because fluctuations in the magnetization are allowed because they don't change the free energy by much. So the system is now prone to fluctuations. It can host more bigger and bigger fluctuations near the critical point. Now if I do include the second term, and first of all my temperature is greater than the critical point, then I have a term such as m squared plus m raised to power 4. Now the second term is positive, which means I'm at a temperature greater than the critical point. Then I get this curve over here, this one. Okay. Once again, the only solution that exists is m equals 0. The only minimum that exists is m equals 0. So when I'm above the critical temperature, the order parameter is 0. The magnetization has to be 0. There's no other choice for the system. So this model, mathematical model, is very good at explaining phase transitions near the critical point at least. Now what if I make this second term negative, which means my temperature is now smaller than Tc? I should get some minimum which does not correspond to 0 magnetization. I should get some finite magnetization, right? So my minimum should not lie here at the 0. It should lie somewhere here or somewhere here. Let's see if that happens. So now I'm going to plot on top of this. I just make the first term negative, say minus 0.5. Now in order to look at this precisely, I need to increase the span a little bit. It's too much. Now you can see this blue curve at the bottom represents a temperature that is below the critical point. So when I'm below the critical point, there is the possibility of having a non-zero magnetization in the sample. You see, this is a solution. This is the minimum to the free energy. This is the minimum to the free energy. And this magnetization, of course, is not zero. It's non-zero. And both of these values exist. So I have a double potential well. The system can either be in this state or it can be in this state. Okay? If I make this even more negative, make this 1. Now I don't want to plot these, I just plot this. See, I can see this double potential value. There is a minimum here which corresponds to non-zero magnetization and a minimum here that corresponds to non-zero magnetization. And since we have a free energy that is proportional to the even powers of m, this is symmetry, this is a mirror plane. It's an even function. Right? So this theory, the Landau theory, is very good at describing phase transitions. The last thing that I would like to talk about today is the heat capacity. So the Landau theory can also predict heat capacities. So if I would like to make this graph, this is the graph for T less than T, greater than Tc, whereas this is a graph for T less than Tc. Now I would like to talk about heat capacities a little bit of a ferromagnet as predicted by the Landau theory, and if this admits a power law of some kind. Now in order to determine the heat capacity, the heat capacity from statistical mechanics we know is given by the temperature, the partial derivative of the entropy with respect to the temperature at constant volume. And it's also given by minus T, the partial derivative of the Helmholtz free energy, the double derivative at constant volume. So this comes from Maxwell's relations, which we learned about in statistical mechanics. So we really have to find a double derivative of the free energy with respect to temperature. Okay, that will give us the heat capacity. In order to do that, first of all we notice the following. For temperatures below the critical point, our free energy is m is 0. Below the critical point, m is non-zero. And m is given by this thing. Or this thing over here. M is A naught over 2b plus minus A naught over 2b half Tc minus T. Half. My temperature is below the critical point, so my sample is magnetized. Now if I insert that value of n into the formula for the Helmholtz function, I get F equals F naught plus A naught T minus Tc n square. Square of this is A naught over 2b Tc minus T plus b, fourth power of this, A naught over 2b squared Tc minus T squared. I'm just finding out the Helmholtz function at a temperature below the critical point. So this is F naught minus A naught squared over 2b Tc minus T squared plus A naught squared over 4b Tc minus T squared. this is F naught plus A naught square over 4B minus A naught square over 2B Tc minus T squared, which is F naught minus A naught square over 4B Tc minus T squared. Okay. Now the first derivative of this with respect to temperature is A naught square over 2B Tc minus T. Right? We just take the derivative of this. Multi do gamma. Now this is at a temperature just below the Curie point. Just below the Curie point. Okay? Now, if I take the derivative of this again, then this equals minus A naught square over 2B at T just below the Curie point. Now above the Curie point, F is F naught because N is 0. Right? So the derivatives are also 0. Alright. So if I were to calculate, if I plot T versus temperature, this is Tc. This is a plot of partial square F over partial T square. What I observe is that below the Curie point, I am somewhere here. This is negative. And above the Curie point, I am here. Okay, so this is how this term is varying. Now my heat capacity is given like this. It's minus T of this, which means that just below the critical point, my heat capacity is the negative of this into the temperature. So it's varying linearly at the temperature. And the slope of this variation is A naught square over 2B. So from the slope of this variation, so this is now a plot of the heat capacity. This is experimentally determinable. You find out the data and you fit the data to a straight line, and you have two parameters. One of the parameters can be obtained from here, the other parameter can be obtained from the Arott plot. That will give you the A naught and the B. This is how you determine the A naught and the B. Now if you plot the heat capacity, below the Curie point it's going up, and above the Curie point it's 0, it drops to 0. So you get this behavior in the heat capacity, the specific heat capacity near the Curie point for a ferromagnet when seen under the light of the Landau theory. When seen in the light of the Landau theory, this is what the heat capacity looks like. This is the theoretically predicted curve. And from the location of this sudden change in the heat capacity, you can also determine the Curie point as well. Experimentally determined heat capacities are of the lambda kind, which means they look something like this. It's called the lambda kind lambda type of heat capacity. It just looks like a lambda. So low temperature heat capacity measurements also give you the critical temperature, and they can give you values of the A naught and the B. And remember, if I look at the first derivative, this is just below the Curie point. If I'm at the Curie point, what's the first derivative? It's 0. So this term is continuous. In the vicinity of Tc, this does not change. This function is continuous. The first derivative is continuous. However, the second derivative is discontinuous. Now, since the second derivative of the free energy is discontinuous, such a phase transition is called a second order phase transition. Now let me show you some plots of the heat capacities that have been determined experimentally. And from here we also observe that in the vicinity of just below the Curie point, this heat capacity varies as Tc minus T some gamma, where gamma is now equal to 1. So you have a power law for the heat capacity as well. The heat capacity is varying linearly with temperature, going up with temperature, just below the Curie point. So now you have a power law, you have a critical exponent for the heat capacity, power law, critical exponent for susceptibility, likewise. So this mean field theories, like the Landau theory, gives you power laws with specific values of the critical exponents. And these can of course be measured, because you can measure all of these physical parameters with respect to temperature or with respect to field. So let me show you at the end some real data from heat capacities. So this data is taken from this particular article, which I have cited at the bottom. Look here, versus temperature, I am plotting the heat capacities. Now, I have only described the heat capacity in the absence of a magnetic field. If you include the magnetic field term, you can find the heat capacity in the presence of a magnetic field as well. So this red graph shows the experimental data for this gadolinium niobium compound as a function of temperature. This is the heat capacity joules per mole per Kelvin. This is the temperature. You see that the transition is around 145 or 150 kelvins. This is roughly the Curie point for this particular compound. The heat capacity is varying linearly. As you are below the Curie point, then ideally it should suddenly drop to 0, but it does not suddenly drop to 0 because of fluctuations. Okay, but the general trend is the same. So it goes up and then it drops. So these green, blue, red, green, blue, pale blue, yellow curves are taken at various magnetic fields. So if you insert the value for the magnetic field inside the free energy term, you can find the heat capacity in the presence of a magnetic field. This is for another compound in which the nickel is replaced by a cobalt ion. Likewise, I've just included these graphs to show that indeed we have a ferromagnet here. On this axis we are plotting the magnetization, we're plotting the temperature here. In the absence of a magnetic field, you see this result, and then the magnetization takes up a power law, goes as something raised to Tc minus T raised to power 1/2 and goes up. So this is indeed a ferromagnet. This is roughly the critical temperature, about 166 Kelvin over here. Okay, and from the magnetization one can determine the effective Bohr magnetons per formula unit. This green graph represents 1 over the susceptibility. This is typical of a ferromagnet. When we studied the Weiss model for the ferromagnet, we obtained exactly similar graphs. This is showing the Curie Weiss dependence of the magnetization. The susceptibility depends on 1 over T minus Tc beyond the critical point. So all of this experimental data fits in really well with what we've studied in this course. Now, different kinds of measurement are done. One is the field cooled measurement, in which you cool the substance in the presence of a magnetic field and then thaw, and then you vary the temperature. Zero field cooled means you cool the substance in the absence of a magnetic field and then vary the temperature. Likewise, you get similar graphs for the cobalt substituted alloy. Now, this is something I would like to talk about in the next class. I would like to introduce the concept of dimensionality. If you have lower dimensional systems, like 2-dimensional systems or 1-dimensional systems, and you have some kind of model, for example, the Heisenberg model or the Ising model, even in those cases you can find out the magnetization. There is going to be some order parameter. Possibly the Curie temperature, the critical temperature turns out to be non-existent or 0 kelvins. So you can never achieve a phase transition in certain dimensions. So I would like to look at the example of this kind in the next lecture. But this is one example of a heat capacity versus temperature for a chain of a single 1-dimensional chain of ferromagnetic atoms. Okay, this is something strange. We should be able to derive this theoretically. This is the heat capacity graph for a ferromagnet, a Heisenberg ferromagnet on a triangular lattice. So we should be able to do some calculations of this kind in lower dimensional systems too. But we will not use the Landau theory. We will use some more sophisticated quantum mechanical models such as the Heisenberg model and the Ising model, and see if phase transitions occur in lower dimensions as well. Maybe not, maybe they do. Alright, so thank you very much.
एंड हो गए सर सर यूएसबी में चाहिए आपको हाँ जी यूएसबी